Hello everyone. Today we're going to be talking about first order RL circuits. More specifically, we're going to talk about how we can use this general solution shown below to find the current of an inductor for any time between 0 and infinity for specifically RL switch circuits. Okay. As you can see, there are 1, 2, 3 unique terms that we need to solve for. This term here, ILT approaching infinity, is the same as this term here. So that's why I say there are 3 unique terms we need to solve for. What are they? How can they be explained? One second. So IL of t approaching infinity, that is essentially the current of an inductor for time approaching infinity in DC steady state. So it's the current of the inductor for time approaching infinity when your circuit is in DC steady state. Okay? IL t equal to 0 minus is IL prior to t equal to 0 in DC steady state. Again, IL prior to t equal to 0. That's why it's t equal to 0 minus. Tau L, that's the time constant for the transient analysis of the first order RL circuit. Okay. How do you find the time constant? Tau L is equal to the inductor. There's only one inductor in the circuit, divided by R Thevenin. What's this R Thevenin that we're talking about? R Thevenin is equal to the equivalent resistance of circuit between the nodes A and B created after removing the inductor and zeroing out your sources and zero out sources. Okay, so what do you need to obtain or to achieve this equation? IL of t approaching infinity, IL of t equal to 0 minus the time constant of the inductor circuit, which is L over R theta. So you need to know R Thevenin or R theta. Sorry, R Thevenin, not R theta. Okay, so let's do an example. This random example that we're going to be using is example 3-9-4. Okay, we are given this circuit where we have a current source, we have a resistor, we have a switch that opens at time equal to 0. We have a resistor down here, a resistor here, and a wonderful inductor there. Here's L, here's our 4, here's our 3, here's our 2, here's our 1, here's I1T, and the current is going downward, IL of T. And we are given that I1 of T is actually constant, and it's always going to be 4 amps. We're also told, is it 4 milliamps? No, it's 4 amps. Let's redraw this. We're also told that R1 is equal to 2 kiloohms. R2 is equal to 4 kiloohms. R3 is equal to 2 kiloohms. R4 is equal to 1 kiloohm. And the inductor value is 0.1 Henry. Okay? Now, the first question, question number 1, is what is the equivalent resistance of the resistor network seen from the terminals of the inductor, assuming switch has been open for a long time. I just realized I need to make a small correction. This R Thevenin is the equivalent resistance of the circuit between the nodes A and B created after removing the inductor and zeroing out the sources for t approaching infinity. That is very important. Okay, so back to this problem. What is the equivalent resistance of the resistor network seen from the terminals of the inductor, assuming the switch has been open for a long time? Wow, very wordy. It's giving me a little anxiety. So if only I knew what that meant mathematically, so I know what in the world am I solving for. You are solving for what we call R Thevenin in time approaching infinity. Okay? And again, what is this R Thevenin? Go back or rewind. It's the equivalent resistance of the circuit between the nodes A and B created after removing the inductor and zeroing out the sources for time approaching infinity. Do you need to remove the inductor? No, not necessarily. I just tell my students to remove it momentarily or in their mind because it makes things easier to see the terminals A and B. Let's do this example so it can all make sense and come together. Steps. We're solving for R Thevenin in units of ohms. 2. We need to what? Remove the inductor, zero out our sources, and just make sure that we are in time approaching infinity. Okay? So, with that being said, we look at the circuit. If time is approaching infinity, where is the switch? Is it in midair or is it closed? Is it open or closed? If time is approaching infinity, we're way past time equal to 0, so the latch has already opened. So, this would be the current source, this would be the resistor, then we would have an open circuit, then we would have that resistor, this resistor, and then the inductor used to be here, right? But not anymore, we removed it. So now we have like A, B, minus, plus. Okay, this is kind of similar to the R Thevenin problems that we've done. So we got R4, we got R3, we got R2, we got R1. We're supposed to zero out our sources, so let's remove this current source, replace it with an open circuit. Now what do we have? We have this circuit. We can remove R1. R1's in series to 2 open circuits. Now we just have this circuit. Again, this is R2. Again, remove this terrible handwriting. What's going on? Too much caffeine. Remove R1 because in series to open circuits, so no current runs through it. No current goes through it. And it's not part of the circuit. I mean, look at it. Take your pen. If you go to the right of the resistor, you can't go anywhere. It's an open circuit. If you go to the left, you can't go anywhere. It's an open circuit. Remove that R1. Now we have the drawing right here. And then we could take it a step further because we notice R2 and R3 are in series. Let's go this way. Now we have this resistor, and this is A, this is B, this is R4, this is R2 plus R3. We could take it one step further, and now we have our R Thevenin, which is equal to what? It's equal to R R4 in parallel to R2 plus R3, which is equal to R4 times R2 plus R3 divided by R4 plus R2 plus R3. Okay? And what does that give you? That means R Thevenin is equal to a value between, depending how you use your calculator and your significant digits, you will get a number between 857 and 858 ohms. Recap, we were given this circuit and we're asked to find, after decoding this wordy problem, R Thevenin seen from the inductor and when time approaches infinity. So we were able to redraw the circuit and zero out our sources, and again assume that time has approached infinity. So the latch is, that's terrible. So the latch is what? Open. Latch is open. And then we simplify the circuit until we got to R Thevenin is equal to R4 in parallel to the R2 and R3 in series. And using mathematics, we were able to get that it's going to be between 857 and 858 ohms. Good job. Question number 2. Technically, I'm telling myself, good job. Question number 2. What is I1 right before switch opens? What is that mathematically? We are solving now for, this is IL. We're now solving for IL at t equal to 0 minus in DC steady state. Why in DC steady state? Because if IL is right before the switch opens, then that means it's been closed for a super long time. What is IL right before the switch has opened? The switch opens, that means the switch has been closed for a super long time. So what is IL of t equal to 0 minus in DC steady state? Steps. First, we're solving for IL of t equal to 0 minus in amps. Second, redraw circuit for t equal to 0 minus in DC steady state. DC steady state, the inductor becomes a wire. Let's redraw our circuit. We have a current source, a resistor. The switch is closed because we are in time equal to 0 minus. Switch closed. Then we have a resistor, another resistor, another resistor. Then we have our wire because we're in DC steady state. Nope, I don't got enough room for the minus sign. All right, inductor is wire in DC steady state. Okay, and this is I1 at t equals 0 minus. This is R1, R2, R3, R4. What do we notice? R4 is in series with the wire. Remove R4. So remove R4 since parallel to wire. Okay, now what do we have? Current source, resistor, 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 wire. This is IL, t equal to 0 minus. This is R3, this is R2, this is R1, and this is IS of t equal to 0 minus. Let's redraw this another way. So this is R3, R2, R1, IS t equal to 0 minus. This is IL t equal to 0 minus. This IS of t equal to 0 minus, it's the one going in and it's going to split at this node. So this, let's separate some of these arrows. This is IS of t equal to 0 minus. is going to split, and part of it is going to become IL t equal to 0 minus. So we can use current divider law. IL t equal to 0 minus is equal to IS t equal to 0 minus divided by R2 plus R3 times R2. Why? Why is this possible? Let's take a little break. If I have a current source, two resistors in parallel to that current source, RA, RB, IS, you have been taught from the current divider law, look at your cheat sheets, look at your notes, the IB is equal to IS divided by RA plus RB times RA. You were taught that because IS is a current that is going to be breaking up at this node. So you'll have a IA, you'll have an IB, and that's the equation for IB. Now, how different is it that if I have a resistor in series to that current source? I don't even need to know the value of that resistor. Take your pen, take your pencil, take your finger. IS is still the one going through this resistor, and it's still the one that's going to break at this node. IS is still going to break at that node. It hasn't changed its value. IS has not changed its value when it went through R because the current source and the resistor are in series. So IB is still IS over RA plus RB times RA. What I just said is too fast. Slow the YouTube video down. But again, if I have a resistor here, the current IS still goes through that resistor, and IS is still the current that is breaking up between RA and RB. So the equation still holds. Now come back here. IS of t equal to 0 minus is the current that's going to break between R2 and R3. Therefore, this equation is true and it holds. IL of t equal to 0 minus. What's IS of t equal to 0 minus? I1. Sorry. I1. Getting too excited. I1. I'm just so used to calling all my current sources IS, but sorry. I1. So I1 of t equal to 0 minus, what was that? It's 4 amps because the current is indefinitely 4 amps. 4 amps divided by R2 plus R3. What was R2? R2 was 4 kilo ohms plus R3 was 3 kilo ohms. Right? I forgot. Why did I make this problem? 4, 2, yeah. And then we got to multiply by 4 kilo ohms. And if you do your math right, IL at t equal to 0 minus is going to be equal to what? 2.6 between 2.66 and 2.67 amps. All right, cool. Recap. So in this problem, we were solving for IL of t equal to 0 minus in DC steady state. And what we had to do was redraw the circuit for t equal to 0 minus and assume DC steady state. The inductor is replaced with the wire. The switch is closed because the switch has not opened yet because we have not yet reached t equal to 0. We're at t equal to 0 minus right before. And we noticed that R4 is in parallel to the wire, so we removed R4. Then we noticed that we had this circuit and we were allowed to use current divider law using this equation, and we were able to get that IL of t equal to 0 minus is between 2.66 and 2.67 amps. Next question. Question 3. What is IL after switch is open for a long time? What is it? Mathematically, we are solving for IL of t approaching infinity in DC steady state. Why t approaching infinity? Because the switch opens at t equal to 0. That was in the problem. Where are you? T equal to 0, switch opens. So the switch opens at t equal to 0, and the switch has been open for a long time, and we're way past time equal to 0. We're at t approaching infinity. So let's try to get this value. Steps. 1, we're solving for IL, the current of the inductor as time approaches infinity, in amps. How do we do this? You need to redraw circuit in time approaching infinity state in DC state, steady state. So again, we're redrawing the circuit assuming time approaching infinity, and we're in DC steady state. So we have a current source, we have a resistor. The latch has been open for a long time. The inductor is now seen as a wire. Here's my IL, T approaching infinity. Okay, real quick. Current is coming from, let's say, I1 of T approaching infinity. Let's say it is. Okay? Does it ever reach the rest of the circuit? No. There's an open circuit here. Don't ask, can the current go backwards? No. There has to be a closed loop. So the current will go through the resistor and then it doesn't go anywhere else. So this resistor and this current source is removed. And now we're left with this resistor, this resistor, this resistor, and this wire. This has no current sources. This has no voltage sources. No voltage sources. Therefore, there's no current going through that circuit. It's just, imagine your protoboard. Imagine you have 3 resistors like this, and imagine you have a wire here. You could say, let's remove this resistor. Okay, fine. But still, there's no current source, there's no voltage source. Current is not going to just be generated out of nowhere. You don't have anything connected to the circuit. So there's no current. The current of the inductor, as time approaches infinity, is equal to 0. All right. Next. This is what, question number 4. What is the time constant in milliseconds? What is the time constant in milliseconds? Okay. Mathematically, we are solving for tau L. How do we do that? Steps. We're finding tau L in milliseconds. How do we do that? Tau L is equal to L over R Thevenin, found in question number 1. Okay, and that was explained in question number 1. If you don't remember, go back early in the video. But if you do your math right, tau L should be equal to between 0.116 and 0.12 milliseconds. All right. Now, last question. Question number 5. What is the current of the inductor at time equal to 20 microseconds? Mathematically, we are looking for IL t equal to 20 microseconds. How do we do that? We're looking for I of L t equal to 20 microseconds in units of amps, right? Yeah. How do we do that? Use the general equation that we learned at the first couple of minutes of this video. IL of t equal to 20 microseconds is equal to IL of t approaching infinity plus square bracket IL of t equal to 0 minus I of L as t approaches infinity, close bracket e to negative t over tau L. And this t is equal to 20 microseconds, by the way. We got all our values. We already solved for IL of t approaching infinity. This was question number 3. Found in question number 3. We know IL of t equal to 0 minus. This was found in question number 2. We already know tau L. This was found in question number 4. So just plug and chug. If you do that correctly, IL of t equal to 20 microseconds will be equal to none other than between 2.24, 2.25 amps. So, what have we done today? We looked at this circuit and we found several things. First, we found R Thevenin between terminals of inductor at t approaching infinity and zeroing out sources. We also found IL t approaching infinity. We also found IL t equal to 0 minus. We also found tau L. And then we were able to find IL t equal to 20 microseconds. All of that, again, the first 4, 1, 2, 3, 4, that's put together to achieve the current of the inductor for some random time between 0 and infinity, using the general formula that was taught in the beginning of this video as shown here. Thank you for joining. Have a nice one.